All right, so our last piece with our solutions has to do with our relationship between light and how it interacts with our molecules. So if we remember from last year, right, we know about the photoelectric effect, where light particles can go and interact with our electrons, right? It's going to make that electron jump up a level, right? So maybe we're going to be a squiggly line there. Electrons jump, right? And then those electrons are going to relax back down. Relax back down and release that energy as photons, right? So we have two equations that go with the photoelectric effect. E equals H nu, right? Nu, we remember, is kind of like frequency, so nu equals F. And we also have C equals lambda nu, okay? So each of these equations are given to us on our equation sheet. H is Planck's constant. It is given to us on our equation sheet. Nu is frequency. Okay. Lambda is wavelength. And E, of course, is energy. Okay, so we should be able to use these equations and do our calculations, going from an energy to frequency to wavelength, or back the other way as well. Okay, but our photoelectric effect, right, we're saying that we are giving enough energy for the electrons to jump. So what we are saying is that UV, or visible light, will make the electrons jump energy levels. Okay, so the electrons, this has enough energy to make the electrons jump energy levels. But just below visible light, with a little bit less energy, would be infrared. Infrared light is able to make the bonds vibrate. Okay? And then even below infrared, we have microwaves. And these microwaves are able to rotate bonds. So the microwaves that we actually have, right, that we use and we think about normally, our microwaves are tuned to emit a certain frequency of light. That certain frequency of light is tuned to rotate the the OH bonds in water, right? It can rotate the OH bonds, and so that our molecules are able to rotate, and it heats up our water molecules within our food. Okay? IR, right? Infrared, the bonds are able to vibrate. And then UV, or visible light, our electrons are able to jump energy levels. Okay? So each of these, we're gaining a little bit more energy as we move up here. And so we're able to do something that's a little bit harder, right? Rotating bonds is super, super easy. Making bonds vibrate is a little bit harder. And then getting the electrons to jump these quantized energy levels requires a little bit more energy, okay? So then, within our solutions, right? Within our solutions, we have these interactions that are going to be occurring, right? But within the solutions, we can look at how much of a compound we actually have in solution based on how it interacts with these different energies, okay? So the different energies that we were talking about, right? Each of these are used in spectroscopy, okay? So we have IR spectroscopy. We have spectroscopy that uses microwaves, okay? And it is able to look at how the molecules are interacting with the light. So the Beer Lambert law is really kind of our simplest way to use our visible light to analyze what's happening with the molecules, okay? So our equation related to the Beer Lambert law is that the absorbance of a solution is equal to epsilon, which is kind of this weird looking little thing, kind of like an E, times B times C. So the absorption of a solution is related to the concentration of that compound that's in there, right? If we have a really concentrated solution that's interacting with all of our visible light, right, it's going to completely block out that solution and absorb all of it, okay? If it is a really not too concentrated solution, right, most of that light is going to be able to go through, and we're not going to absorb most of the light, okay? So epsilon, right, this is the absorptivity constant. Constant. I can spell. There we go. So epsilon is the absorptivity constant. This is oftentimes just a number that we completely ignore, okay? It's unique to each compound, so if we use water in our solution, we'll use the absorptivity constant for water. If we use I don't know, maybe hexanes with our solution, we would use the absorptivity constant for that. But most of the time, we're going to be comparing water to water to water with different concentrations of something else. So that absorptivity constant is going to be the same all the way through. Okay? B here, I'm going to bring that over here. B is the path length. So when we do our Beer Lambert law calculations, right, or our measurements, we oftentimes use that cuvette. That cuvette is 1 centimeter in length, right? So this is 1 centimeter. So 1 centimeter, we're multiplying times 1, we can ignore it again. Again, we're not changing it, so we oftentimes do not care about it. So really what that ends up meaning is that our absorbance is proportional to our concentration. So if we create a graph of concentration versus absorbance, right? So let's do actually concentration down on the bottom, absorbance on the y-axis. We should have a 0 point where our concentration is 0, so the absorbance that is changing by that should be 0. And then we should have a linear line where the more concentrated we get, the more absorbance we have and the less light that gets through it, okay? So we can also do this as a transmission graph, right? So transmission would be a percentage, okay? And so our transmission would start at 100% up here when we don't have anything, any sort of compound in there. And then as we add more of our whatever is absorbing the light, right, the transmittance is going to go down, okay? So what we will do is another lab so that we can understand and graph this and understand that concentration, right, as concentration increases, our absorbance should increase as well, okay? That's all we've got for this unit.